Okay, so I'd like to tell you about a certain generalization of Pebble or Ehrenfeucht Freise games in the context of model theory. Um, Next slide. Okay. So first, I will say a few words about model theory. Professor Hampkins already spoke about this subject during Stack 4, so I will only briefly reiterate the central idea. And then I will discuss an enrichment of model theory where one introduces the actuality operator. And then we'll move to Pebble games. I will say what a classical Ehrenfeucht Freise game is and what it's all about. And then we'll move to the model variation of it with actuality. Okay, so yeah, model theory with a nice picture. Stolen from John. So consider a potentialist system M. So for example, the class of all models of some first order theory T for some language L. And we'll say that model M extends to model N, just is in case M is a submodel of N. And this is like within this potentialist system M. And we say that possible phi is true at M if it extends to some M in which phi holds, and necessarily phi is true at M if phi holds in all its extensions. And here we have an example of a formula in the model language of graph theory. It says that vertex X is connected to vertex Y. And the idea is to use this necessary C that sort of detects the connected components of X, the connected component of X. Okay. Okay, so now let us turn to the actuality operator. And here we'll need modification of satisfaction relation. So let us denote terms and relations of L by taus and Rs, respectively. We let S to be an assignment function, but in this case, we not only map variables V's to individuals, M's, individuals of words in this multiverse sense, not only one model, but words. We map word-like variables, so variables but for words, to words in M. And we define the satisfaction relation in the standard manner, but there are a few modifications. So when we take care of equality of terms and relation on terms, we not only need the obvious things like that interpretations of terms needs to be in Rm, but also those terms, those interpretation of terms need to be defined. So normally that's guaranteed, but here we have these various words and we will jump from one word to each other and we might be left with some individuals, for example, that are not from the current actual word. And so we need this little trick. Okay, so possibility operator appears again. This time it's with sub V, and this is just to detect, to sort of bookkeep the word variable associated with the word we are extending to. So this is nothing surprising. And finally, we have the meaning of the actuality operator. So this just means that if M satisfies actual sub V phi of S, then that means that the word that S maps V to satisfies phi of S. Yeah, and here we have an example of a sentence with the actuality operator. So it asserts that necessarily there are two possible words, such that every individual who is tall in one of them is short in the other. So just like an illustrative example. Okay.
Can I ask you a question? Can you could you please maybe explain the actuality operator again quickly? I just didn't understand.
So can you see my mouse or?
Yes.
Okay, so we have these various words in the potentialist system or the multiverse, if you like, and so M satisfies actually sub V of phi when this word that is being associated with actuality operator satisfies phi. Does that make sense?
Well, I don't understand right now, but that's okay. Maybe just continue.
Maybe Joel, can you help me?
Yeah, the actuality operator allows you to make truth assertions about worlds that had arisen previously in the formula. So maybe earlier you had said possibly something is true, and then you said necessarily and so on after that. But you want to go back and talk about that original world. So actual sub W means in W it's true, even if that's not the world that you're currently talking about in.
Thanks.
Yeah, good. Thank you. Okay, so let us move to pebble games. So we have, this is like the classical pebble game. So we have two structures, M and N, and we have a game of perfect information played as follows. So player one chooses an element of either M or N, player two answers with element of the other structure, and then they take rounds and they choose elements. So for example, player one chooses M1, then player two needs to choose N1, then maybe player one chooses N2, and then player two has to choose an element from this other structure. So at case stage of the game, we have tuples over line M and over line N of length K, and we say that that if for every K less than omega M and N together with those chosen elements satisfies the same atomic sentences, then player two wins. And we have the theorem, also classical theorem, that if player two has the winning strategy, structures M and N are elementary equivalent. So now let us move to the model case. So let me describe a model analog with actuality. We have two actual words, M0 and N0, in the potentialist system M. And as before, players are picking points, but not only points, but we also can have extensions. So player one may decide to extend one of the structures. And player two must respond with the same type of a move. And after we take points from these expanded words, and the winning condition is a little bit different. At each round, we have to have the same atomic sentences in the current actual word. So before we had only one, like we didn't have extensions, so we were concerned only with two models. Here we have like at each step, we are concerned with current actual words.
Sorry, Wojciech, can I ask a quick question?
Sure.
So you, when playing around where player one plays to expand the world, they just expand the world rather than also playing a point in that expanded world?
No,
or does it not matter?
I think it actually matters because you can. I think it matters. So yeah, it is a separate move. You expand, and that is your move.
Right. Okay. Thank you.
Okay. So then we play points at that extended words. Okay. So player one maybe extends again. This time the red structure. Because he has like he's free to extend blue or red. There is no requirement that it needs to be blue. And player two needs to play a symmetric move. Okay, so of course I've been drawing these dots on these extensions here, but when we extend, it's like the whole structure here. So the new points that they play can be on this part on the bottom here. Also, I want to make that clear. So we can have them here, but we don't have to. They can also be on this added part. And then, whoops. Okay, so now another move that is allowed is to declare one of the previous words as actual, but something interesting happens. We are left with those elements here. And that might be worrying, but it's actually okay, because even if we now have individuals outside the actual world, we can still make meaningful statements about them. And that's because we defined satisfaction in such a way. Okay, player two responds, and we play elements, the player goes on, another extension, and on. Okay, so this is the game. It's fun, maybe. But then, well, so what? So there is, of course, a theorem that generalizes the first order case. So if player two has the winning strategy, structures M and N are elementary equivalent with respect to the full model language with actuality. So we now have elementary equivalence, but with respect to the full model language. So the classical theorem generalizes. And what I'm doing right now is working on the details of the converse and on the version for infinitary model languages with actuality. These all are known for first order case, and we suspect that there will be also higher model analogs of them. Okay, so thank you. And if anyone wants references, it's here. So thanks very much.
Are there any questions or comments?
I was wondering, for example, you look at countable models only in some settings, or what kind of models you typically look at?
In model theory, we sometimes look only at countable models, but like the idea is very general.
Okay, this is a very general theory.
it sort of allows you to formulate sentences that model theories are already talking about, like, is there an embedding where something is true and so on. So it's very natural thing to do.
Okay, thanks. I guess I meant because in the countable case, from the Ehrenfeucht-Fresse game, you already get isomorphism. So I guess
Oh yeah, yeah.
the theorem is very general and talks about all kinds of uncountable structures also.
Oh yeah, that would be also interesting to look at how it looks in the model setting.
I mean, in the classical case, at least, I don't know. But yeah, okay.
Yeah, thanks.
I have a comment. So I looked at these modal Ehrenfeucht-Fresse games without the actuality operator. And, so I did get a result, which is the analog of what you wanted, which is that there's a winning strategy for player 2 if and only if they are elementary equivalent with a full infinitary language. And that's also the same thing as there being a bisimilation between the two, where you generalize the notion of bisimilation. It's a generalization of both a bisimilation and of a back and forth system.
Oh, that's great. I will steal the proof from you.
Sorry, what?
I will steal the proof from you.
Okay. So yeah, maybe there's something like this. Maybe you can find a similar analog of bisimilation, but when you're also talking about actuality, and then that might help you to bridge the gap between these two things.
Yeah, we definitely talk about it